Hey METC 107 students, welcome to our first actual lecture for the semester. So we're going to be talking about what is technical graphics, what is the design process, and really start talking about technical drawing and documentation and this language that engineers speak through the form of drawings and pictures and 3D models and documents. So just kind of a quick catch up on what you should have done to this point. So if you go into our modules button in Ivy Learn, before you watch this video, you want to make sure that you went and watched the welcome video that I made that kind of gets you acclimated to the class and tells you everything you need to know about entering METC 107. So if you haven't already, go back and watch the video in the Start Here module that will tell you everything you need to know as you enter into METC 107. The other thing you should have done by now, hopefully, is introduced yourself to the rest of the class. So that's really kind of your first assignment for the semester, is to watch the welcome video and then go through and just do a quick introduction of yourself with those questions that I posted and kind of get to know everybody else that way. So if you've done those two things, you're ready to start. I also did recommend that you guys go to the Home tab and download Autodesk Inventor. Although you don't technically need it yet, it's a good idea to go ahead and download it. And then also download the Zoom client for our face-to-face Q&A meetings that will happen later on in the semester. So really those four things you want to make sure you've at least done or started before watching this video. So if you haven't and you need to, go back and do those and then come back to this one. And if you have done them already, you're good to go. Let's talk about technical documentation a little bit. So this is going to be kind of a shorter lecture because you've gone through and watched that welcome video already. But let's talk a little bit about what are technical drawings, what's the documentation process, why do engineers make drawings? If you want to follow along with my lecture or go back and refer to it at any point, there will be some videos that I want you guys to watch that are in the lecture. You can download the PowerPoint right here by clicking on this, as well as anything else that I post in Ivy Learn for you guys will be in the modules. So let's talk a little bit here about what are technical drawings. Okay, so some things we're going to look at really quickly here. Just a broad overview of technical drawing. What is it? Why do we do it? What is the design process? If you're interested in this as an engineer, what are some of the career possibilities? And what do employers look for out of a person that works in a job doing technical design or technical drawing, or some people call this industrial design sometimes. What's an employer look for? And job prospects. Are there jobs doing this particular type of work related to engineering? All right, so let's talk about technical drawings first. What is a technical drawing? Now, there are different forms that these things can take, and we'll talk through some examples and I'll show you a few. But really, anytime an engineer makes a drawing or a design or a 3D model for something, there's three reasons they're going to do that. And you can see I've listed these here. So the three reasons are visualization, communication, and documentation. And those are important things to keep in your mind as we go through this class. Those are the reasons that we're trying to invent or design or create this stuff. Okay, so visualization, what does that mean? Well, you've probably heard the phrase, a picture is worth 1,000 words. So one example that I have for visualization is the instructions that come with a kit of Legos. So I love Legos. I don't have a ton of them. My sister and I had some when we were kids and we used to play with them. I've still got a few of the ones that I had from when I was a kid. I got a really cool, like a little pirate set. And my daughter has some too now, since she's 6 now. She's kind of getting into them. But anytime you buy a set of Legos that's supposed to make, something specific, not just a generic set of blocks, but it goes to build something, they come with these instruction sheets. And a lot of people think of these as, yeah, they're instructions, but they're technically more than that. They're technical drawings. So, and they're kind of unique because they don't have any words in them, or very few words. So these are a great example of documentation, right? If you look at these things, they specifically allow you to visualize what you're trying to build. And so this is a great example of a technical drawing in practice, but it's a picture is worth 1,000 words. You can put this thing together, and it's actually kind of an intricate thing to try and do. Imagine trying to talk someone through this. If you didn't have a drawing to give them, how complicated the instructions would be to try and have someone even just build something out of these plastic Legos. Trying to explain to them, the ins and outs of how these pieces fit together and how they look different and which one should they pick up and how does it connect to the other ones that they already have. It would take you an hour and a half to try and explain to somebody how to build this thing. But if you could just give them the instruction sheet, they could probably build the thing in 5 minutes or less. So Legos are a great example of technical drawings or any kinds of instructions. I know if you've ever been like to IKEA and bought furniture from IKEA, they are sort of in the same idea of this. So they come with their instruction packets that have very few words in them, but they're technical drawings. They're there to visualize. Okay, another thing that we do with visual, or not just visual, but with technical drawings is communication. Okay, so really all of these are communicating, but they communicate in different ways. So obviously this first drawing for the Legos that we looked at, it communicates how to build this little watermelon slice. If we look at an architectural drawing like this, like a floor plan, this communicates different things. So, you know, this floor plan, this communicates to a contractor maybe where the walls are supposed to go or where things sit in relation to one another on the floor plan, okay? Maybe, you know, what's the fire rating for a wall or a different wall type, or maybe what's the distance on the inside of the room from the inside to inside on the walls. Okay, so you can see on this architectural plan, there's all kinds of information on here. They've got different note bubbles on here that maybe tell what kind of door is supposed to be installed inside a frame. Is there an undercut on the door to allow air to transfer through? Is there a window in the door or not? So there's all kinds of information that can be transferred, some just by pictures and some with pictures and words, or some just words. But you'll see a lot of times on drawings, it's a combination of pictures and words to try and communicate information as clearly as possible. Okay, so that's a communication piece. Then you could look at this drawing. This is an example of an exploded drawing. You see these a lot for parts diagrams where they show people, you know, here are all the pieces in an assembly and here's how they go together. So this is sort of like a mechanical version of Legos, right? It shows somebody, here's all the pieces that go together in this thing and here's how you take them apart and here's how they go back together. I mentioned to you guys earlier that I'm trying to change out the head gasket on my MR2, which you can see I'm in the middle of. I showed you this earlier in the Start Here video. But I've looked through lots and lots of these different drawings on Toyota parts diagrams, trying to find all the little fasteners I need for my car as I put it back together. And there's lots of these exploded diagrams. And what they do is they allow you to look at all the individual pieces. So I can go to Toyota's website and I can say, okay, well, I need 2 exhaust studs because the ones that hold the exhaust manifold on were so corroded and the threads were all messed up, and so I'm going to take those out and put 2 new ones into the cylinder head before I try and put the exhaust back onto the cylinder head. And I need a gasket to go in between there, and there's all the little nuts and bolts that hold the exhaust manifold to the cylinder head. And all these things have their own different part numbers and their own unique prices and whether or not they're even available anymore. And so you can go through a parts diagram like this and click on these things and figure out, are they available? What's the name of it? How much does it cost? Is it in stock or not? How long is it going to take me to get it? Where's it coming from? What's the shipping cost? And so for very intricate assemblies like this, you can start to pick out exactly which piece you need. So imagine, you know, if you call up somebody at a parts counter and you say, hey, I'm working on this hub assembly for, you know, a motorcycle or a bicycle or a moped or, you know, whatever this is. This looks like it's off of a motorcycle or a moped or something maybe. You know, if you call up and you say, hey, I need the hex head nuts that go inside the hub assembly. Well, even just on this drawing, look how many there are. You know, there's 2 or 3 or 4 of them over here. There's 1 in here, or 2 of them in the middle. There's a couple more over here. Sometimes words aren't enough, right? You got to have that picture. And so you can click on that and instead you can tell them, I need this part number. And you know when you give them that part number, you're getting the right part. And you're not going to have confusion or, you know, something that's lost in translation as you try and communicate from one person to another. So drawings are a great way to make sure that everyone's talking about the same thing and make sure that people know how to put things together and make sure that information is being passed clearly from one person to another. So these 3 things right here are really kind of the reason that we have this class in our curriculum and the reason that we're trying to teach people how to make 3D models. All of it in the end is a reason, or it's a way for us to try and pass information from one person to another without mistakes. And the trick is we're trying to pass information about highly detailed, very intricate things. And we don't have room for mistakes. So technical drawings are the communication language, or one of the communication languages that engineers use, and we use it very heavily. So it's important that you understand how to speak that language, that you can look at a drawing and interpret it, but you can also write that language, right? Not only can you speak it, but can you write it? Can you create those 3D models on your own? So this technical drawing language is one that engineers need to be able to both read and write. Okay, can you look at a drawing and understand it? And can you write your own drawings or 3D model your own pieces and put them onto a drawing page and share them with other people? And that's the goal of this class, really, at the 40,000 foot level, is can we read and write this language of technical drawing? Okay. So where did this come from, this idea of technical drawings? That at some point somebody had to be the first person to realize, hey, let's put this down on paper and share it, right? So we don't know exactly who did it, but there are a few people that are very important in this idea of documenting things on paper from either an architectural or a mechanical standpoint. One guy that gets probably the most credit is Filippo Brunelleschi. So he's the guy that discovered linear perspective, which basically means if I have a 3D object and I have depth perception, when I look at that with my eye, we know as humans that if we look at something with our eye, if it's farther away because of perspective, it's going to be smaller. As things get closer to us, they appear to get bigger. When in reality, they don't, right? If I'm far away from you, I'm not actually shorter. I just look smaller. And so Brunelleschi realized, how can we take that and make a drawing that is measurable and scalable and put it onto paper? And so he's one of the guys that came up with the idea of linear perspective, and he gets credited with it typically. That was around the year 1425. So this idea of scaling things and drawing them and putting them on paper has been around for plus or minus, 600 years probably. So it's not a new idea. But he's probably the one that gets a lot of the credit for it. I do have a little video I want you guys to watch here. So if you download the PowerPoint, you can click on this. It's kind of a cool little thing that it teaches you a little bit about Brunelleschi's personality. He was not well liked by most people. He was very abrasive in personality, but very intelligent also. So he's one of those people that kind of was hard to get along with. Very, very intelligent, but kind of shot himself in the foot a lot just because he couldn't get along with other people. And this is a short little video, probably 4 minutes, 5 minutes, that talks about some of his life accomplishments. He has kind of a very interesting life, but it'll teach you a little bit about some of his shortcomings and some of his strengths and weaknesses. So I highly recommend you watch that short video just to learn a little bit more about Filippo Brunelleschi and some of his how would you say it? I guess his contributions to society and his contributions to engineering and technical drawing. The other person that I'm sure you've heard of is Leonardo da Vinci. He gets credit with some of this really from a little bit more artistic standpoint, but he's one of the first people that started really like documenting his ideas and inventions on paper. And so we've all probably seen all these different inventions that Da Vinci sketched out on paper, some of them feasible, some not. But he gets a lot of credit for combining art and science and technology and invention all together. And for the first time, he starts to kind of put out these schematics on paper of, hey, I've got this idea, and if I drew it, I can't show you in my brain what it looks like, so let me use my artistic skills and put it on paper and try to help you understand this crazy idea I have in my head that may or may not actually work, but if we could, here's how it would work. And so he's the guy that kind of gets the idea of how do we put concept sketches onto paper and share our thoughts with other people by drawing them. And so he gets a lot of credit also during the late 1400s for showing people how to document things on paper and pass information that way. Now, more recently, we've kind of made a transition in the last 30 or 40 years in technical drawing from hand sketches to computer-aided design. So I did throw in a little video in here. This is, pretty long. It's probably about an hour if I remember right. I don't intend for you to watch this whole video, but watch a couple clips from it because I want you guys to see prior to computer-aided design. I'm just going to open it up here really quickly. Prior to computer-aided design, how were technical drawings created? And they were created by hand with a pencil and paper on a drafting board and with drafting tools. So this is kind of, oops, looks like it's been shut off. Maybe you can't find that anymore. I may go back and try and relink it. But prior to 1940, or not 1948, prior to about probably the the 1980s seemed really like the switchover period when people started getting heavily into computer-aided design. Prior to, like the mid to late 80s, lots of work, or pretty much all work, was done pencil paper. The 80s saw the onset of computer-aided design, really, and computer-aided drafting. And throughout the 90s, we saw it get more and more and more popular and more prevalent until modern day, when very little, if any, design is actually done pencil and paper anymore. Ideas are still shared that way early on in the planning stages, but no production work is really done pencil paper anymore. So everything's done with computer-aided design now. So in modern day, how do we use CAD to help us design stuff? So first off, technical drawings and, more importantly, 3D models play a huge role in the design process. They allow us to do a lot of different things. So one thing is they allow us to share design options with our customers or clients. So as a designer, you may have 2 or 3 options, and you want to help your customer weigh those options, and they can tell you, or maybe not even your customer, maybe your supervisor at work, show them, hey, here are the 3 best alternatives that I came up with. What do you think? And you can start to have a discussion about those things, even though none of them technically exist in the real world yet. They also allow you to avoid potential problems ahead of time. So you can see, do the bolt holes between 2 pieces line up? Do they fit together the way we think they're going to fit? Or you could do a kinematic analysis and see, this assembly that I've invented is supposed to move around. What's going to happen when it moves? Does it mesh nicely, or is it going to hit itself? And so I'm looking at my bicycle across the garage here, and something like that, you might do a kinematic analysis on it in CAD software and see, when this bicycle rotates around, when the pedals rotate around, are they going to rotate freely, or are they going to get, halfway around and then the pedal hits the bike frame on the back because, the dropouts in the back of the bike for the back wheel, they're too wide maybe, and when those pedals go around, they hit the frame. We didn't plan on that. You can see that stuff in CAD software ahead of time and fix it before it becomes a problem. And we'll learn how to do that in Inventor, both in METC 107 and in METC 220. But that's part of what you do with CAD software, is you try to anticipate problems before they happen in the real world and fix them when it's cheap and easy on the computer. We can also do 3D printing, where once we have a design that's pretty far along in the design process and we're happy with it, we can make a prototype of it. And 3D printing is a way to make a cheap, affordable, fast prototype where you can do some more checking and testing and see, okay, we have this concept that theoretically works on the computer. How does it work in the real world? And there's no substitution really for holding something in your hands or seeing it in the real world, that things don't always look or feel in the real world the way you think they will when you look at them on the computer screen. So 3D printing is a way that we can take our designs and bring them to life and compare our CAD model to the real thing at a relatively low cost. We can also use our CAD software for predictive failure analysis. So something like finite element analysis, which we'll do in METC 220. We could take a CAD model and try and test it and break it and see, is it as strong as we think it should be? Or where is it most likely to fail? And so you can start to do failure tests and stress and strain things and see, where are they going to break, or where's the weakest area in a part. Okay? And we can do that through simulations in our CAD software. So the people that do this work are typically termed drafters or designers, although I sort of feel like, being involved heavily in the CAD industry for the last 6 to 8 years teaching design technology, I really feel like the term drafter is sort of dated. I think that the days where someone is going to be strictly just a computer-aided designer are probably disappearing over time. Most engineers and architects know how to use their own computer software now. They don't have a separate person to do that for them anymore. And so I think the days of working as a CAD designer or a CAD operator without some kind of technical training beyond that are probably starting to disappear. Most engineers that I know now just do their own design work. They don't have a separate person to run the computer software for them because they already know how to use it. So drafter or designer is a term used, though, for someone that works exclusively in CAD software as their job function. So moving on, there are different categories of drafting and design. We will work in one of these this semester, but there are kind of different categories or families of this. So one is architectural drafting or architectural design, where you do construction projects. Now, just because you're a mechanical engineer, does that mean you won't end up doing this? No. This is probably the area that I worked in the most as a professional practicing engineer. I was not formally trained in architectural drafting, but I kind of figured it out as I went. But as an HVAC designer and a mechanical designer, I did quite a few architectural prints. But even though I was a mechanical engineer, I kind of stumbled into this. So you can do architectural drafting or design. This is what we're going to be doing this semester, is mechanical drafting and design. So I've got a video down here you're welcome to watch. Kind of goes into a little bit more detail about what this is. But this is sort of the idea of documenting pieces and parts and assemblies and how things fit together and how they're going to be manufactured. So, what material is it made out of? What kind of tolerances does it need to have? How does it fit together? How are we going to make it? Or maybe if we're buying some of the pieces in the assembly, what vendor is creating them and where do they come from? And what's the lead time and the cost and all this different stuff. So it's basically, if you want to build one of these pieces, let's say we want to make this little triangular bracket from scratch, we're going to learn how to make technical drawings that tell us everything we need to know about creating this thing from scratch. Think of it like an instruction or like a cookbook almost. It's sort of like the engineer's cookbook. Okay, that's mechanical drafting. And we can also have civil drafting. This is more for infrastructure projects like plumbing, wastewater, roadways, bridges, railways, parking lots, subdivisions. You see a lot of times in Indiana where they take farmland and they'll actually plot it out and turn it into a subdivision, and they'll build houses on it. So that work preliminarily would all be done by a civil engineer, where they would figure out how to lay out that subdivision. How big do each of the lots need to be for the house? Where does the road go? How wide does the road need to be? Where do the sidewalks go? What are the code requirements for a sidewalk to make it, meet requirements? Where do the manhole covers go? Where do the drains in the street go? So when it rains, the water has a place to run off. How do you slope the roadway to make the water run off to the sides? So there's all kinds of stuff that goes into civil drafting and civil design that we take for granted because it just works. But if you look around you, there's lots and lots of things that from an infrastructure standpoint have to be designed by civil engineers, and we take a lot of them for granted because they just work and we walk past them and we kind of ignore them. But civil engineering and civil drafting is a whole other branch of engineering, but they do create technical drawings just like we do, so I want to mention their category at least. And then our last category, which is electrical or electronics drafting. There's kind of two categories: electrical typically meaning high voltage, and electronics usually meaning low voltage or DC systems. These are probably the most complicated, at least to me, because I know the least about them. But this is where you're going to see, for instance, diagrams on maybe, if you're looking from an electronic standpoint, you might be seeing diagrams of like printed circuit boards or wiring diagrams maybe for how different components are going to be connected together. So just like when we design a mechanical system, well, electrical engineers need a language they can speak also as they design their products. And that would take the form of an electronics or an electrical blueprint or technical drawing. Okay, so we've looked at the different categories. First we looked at why do we create technical drawings. We looked at the different categories. So what about software? What's everybody using to make these drawings? Well, the answer is a little bit of everything, unfortunately. That the world's a messy place and nobody ever agrees on the same thing. So we have lots of different software that gets used by various industries to create their technical drawings. And I put some of the most common or most popular ones up here. From a mechanical standpoint, the biggest one is probably SolidWorks, the biggest single software package. We use Autodesk products pretty much on Ivy Tech campuses. So SolidWorks' big competitor is Inventor. Inventor has a pretty big market share, just slightly smaller than SolidWorks. But Autodesk also has another program called Fusion 360 that we may look at a little bit this semester. It's very similar to Inventor, but it's kind of cloud-based, and it's kind of a from-the-ground redesign. Other softwares might be Creo or what's formerly known as Pro-E. That's another popular one. CATIA. There's one called Siemens NX that's pretty popular, like in aerospace and automotive. So The big ones, though, if you talk to people about mechanical design software, the big three really that you're going to hear about are SolidWorks, Inventor, and probably Fusion 360. Those are the most common ones. They have the biggest market share. Okay. Then, of course, you've got good old AutoCAD. AutoCAD is just a 2D drafting, like a flat blueprint or flat 2D design. You can do 3D modeling in AutoCAD, but nobody does it anymore because it's an awful way of 3D modeling, at least in my opinion. It's clunky, it's slow, it needs redesigned. There's just so many better options for 3D modeling stuff. But AutoCAD, good old AutoCAD, has been around forever for 2D drawing and 3D modeling, but nobody uses it for that. If they are, you probably need to run away from them. So if you go to a job interview ever and they're using 3D or they're doing AutoCAD in 3D, run away. You don't want to work there. It means they're like 30 years behind the times. So architectural and civil engineering, these are some programs that you'll see used there. So Revit is by far the most popular architectural software. Autodesk Civil 3D is really popular for civil engineering. You might see some other smaller architectural programs like SketchUp or Chief Architect. But for the architectural industry, Revit kind of has a big foothold on the architectural industry. So the two big ones for architecture really still are AutoCAD and Revit. They're kind of the two go-tos. But these are a bunch of different software programs that you probably will hear the names getting tossed around. Sorry, I gotta get a drink of water here. All right, so let's say you're interested in doing this job function as an engineer, because a lot of engineers do CAD design at least part of the time, if not all the time. If you go for a job interview where you might use one of these software programs, don't be surprised if they give you a CAD test when you get there. This kind of catches some people off guard where you go to a job interview and you have the sit down where you talk to somebody and they go over your resume and your school experience and all that kind of stuff. And after you go through your transcript with them, maybe they talk to you about what your career goals are and your strengths and weaknesses, and then they might say at the end of the interview, okay, well, we just want to give you a CAD test. And people a lot of times are caught off guard, like, CAD test? What kind of job interview is this where you guys are giving me a test in the middle of the job interview? I didn't expect this. So the reason they do that is not because they want to try and trick you. It's because you would be surprised if you go through a stack of resumes, how many people lie on their resume just to get their foot in the door. And they don't understand that it's really not a good strategy to get a job, because if you put something on a resume, someone's going to expect you to be able to do that stuff when you go for the job interview. Don't put things on your resume if you can't actually do them. I've had a lot of people come to job interviews and they put stuff on a resume, like even CAD programs. We interviewed somebody one time at a job where I was working, and they had some software on their resume, and we asked them what they knew about it, and we figured out pretty quickly during this job interview that they didn't really know anything about the software. And through our conversation, they basically told us that, yeah, I have it installed on my computer, but I haven't really used it. And so, like, why would you put that on a resume, right? Just because you installed it on your computer, you don't know how to use it. So be careful what you put on your resume. You don't have to be the world's, greatest master of this software program, but you need to be able to use it to a functional level. Right? You don't have to be a total complete expert, but yeah, I can get around. I can do the basics. I can do some intermediate level difficulty stuff, and I know how to figure out things if I am not good at them yet. Okay. But with that being said, the number one thing that we've heard from employers in any kind of technical position is that they value soft skills also very highly. So employers, yeah, they're looking for those hard skills like technical skills, and those are very important. But what a lot of employers tell us is, well, we just want somebody with a good foundation. We'll teach them anything else they need to know. We want someone that has good soft skills. And so they are more interested a lot of times in someone that has a good foundation of technical expertise, but someone that will come to work on time. They don't call in sick all the time. They get along well with their employees. They have good communication habits. They answer emails. They're courteous and professional. They dress well. They come to work clean. They've got their hair cut, stuff like that. They dress nicely. So these are soft skills. And believe it or not, these are the ones that employers have the most trouble with. Sometimes it's harder to find people with good soft skills than it is to find people that are good at the technical part, which is kind of weird. You wouldn't think that, but it's the truth a lot of times. So these are some questions that I threw up here that you might hear from a possible interview someday if you're interested in a job in a technical field. These are the types of things you get asked a lot, right? So job prospects. If we look at job prospects, I'll show you a couple of websites you can use. So these are, websites you can use if you're specifically looking for a job. A CAD designer, typically in Indiana anyway, and this is not engineering, this is just CAD design, which there's kind of two different terms there. If you're just working as a CAD designer and you don't have an engineering degree, you could expect to make maybe, 40 to 60,000 somewhere in there starting out with a 2-year degree. If you have an engineering degree and you're taking on more of an engineering role, that's obviously going to go up. It can also change depending on where you live. But my favorite website, if you're looking up job statistics, is bls.gov. This is the Bureau of Labor Statistics. So you can look up drafter on here, for instance. So we could look up mechanical drafters. That would be someone that just uses mechanical design software for their job. This is different than being a mechanical engineering technologist. That's completely different. So this is just CAD design. You would not have to have an engineering degree technically to do this. This would be more probably similar to our design technology degree. But if you look through, here's some different statistics about working as a designer using CAD software. So most people doing this job are going to make, in the $50,000 to $55,000 range probably. You can obviously go lower than that, and you can go much higher than that, but it depends what you're doing and where you're doing it at. The median is going to be around $55,000 probably. If we go down, they've also got, how many people are employed in that area. So it sort of shows you, think of these graphs as like the density or like per capita, how many people do that job. And so really what you can see is there's a lot of manufacturing around the Great Lakes. So, those engineering or technical jobs are going to be really in demand anywhere you have water because of shipping and receiving, and because of shipping and receiving by, land or rail or waterway. Most manufacturing and most technical jobs locate themselves next to water or next to a coastline. So, the Great Lakes are kind of a hotbed of manufacturing, and because of that, there's a lot of engineering jobs and a lot of technical jobs around the Great Lakes, and Indiana's no exception. So that just kind of shows you, what's the possibility of a job there. So here's kind of a map of mechanical drafters in the United States from, 3 years ago, roughly. And you can see Indianapolis is right here in the middle. So we've got a pretty big grouping of people there. So according to their stats, the annual mean wage or the average for our area is about $58,000 a year. You can go up like to Chicago. You're going to see it goes up, 61,000 because it's a bigger city. If you go out to the West Coast, you're going to be making about 65 out there, but the cost of living is much higher, obviously. So, it just depends where you live and what you're doing. So I love the Bureau of Labor Statistics, though. Like, I can lose hours on this website just searching out things about different career fields. And again, the screens we're looking at here are just for drafting and design, just for CAD work. This does not count if you have an engineering degree. So if you look up engineering technology or technologist on here, you're going to find a completely different set of statistics for that. Which is going to look similar, but you're probably going to see the wages are higher because the training and the degree requirements are higher. So just some info there about looking for jobs and drafting and design in general. Let me get back to where we were here. Okay, so running through really quick, I'm going to put this in like hyperspeed here just to kind of run through some stuff. Okay, so we talked about job prospects. Let's talk really quickly about traditional drafting tools. And then we'll talk about what your homework assignment is for this week, because you've watched a lot of video at this point from me this class session so far. So traditionally, where did we come from on some of this stuff? So we talked about in the olden days, everything was done with drafting by hand on a drafting board. So this is an example of an old school drafting room where these are like your predecessor to a CAD designer. These were the guys who would just sit and draw stuff all day, and they would draw big blueprints actually to scale by hand. So that's been replaced obviously with the computer. So hand sketching is still a useful skill. It doesn't get used as much as it used to, but it can be handy from time to time still. But most of our design work now is done on computer. So, this is sort of like the drafter's computer. Before CAD work, we would do our work on a drafting board like this. So just so you kind of understand this stuff from a historical perspective. We still use technical pens and pencils. So finding a good pencil you can draw with is still nice. They come in different widths, obviously. We're most commonly associated with the 0.7 millimeter pencil. I mean, like a Bic mechanical pencil, that's what it is. Find one that works for you though. I like a heavier lead, like a 0.9 when I draw, because I write really heavy. But they come in different widths. You can also get them in different hardnesses. So some leads are softer than others, I guess, if you're going to draw a technical drawing by hand. And they're rated by like an H or an HB number, which most people ignore this. They've never really paid attention to it before. But hard leads will last longer. You have to sharpen them less. So they're good for things like a graph maybe. If you're trying to make a really precise graph and you want your pencil to stay sharp, you're going to use a harder lead. And the higher the number, the more it is. So the hardest lead is a 9H. And then if you go the other end, the higher the number, the softer it is. So like a B lead, the soft leads, a 7B is the softest. It's almost like a crayon. It smudges really badly. You don't really want to draw with it much. It's really more for artwork. But you can get leads in different diameters, and you can get them in different hardnesses. So most common pencil lead that you buy, like if you go to the store and buy one of these packages of lead, it's a 0.7 diameter and it's an HB, which is kind of in the middle. It's right in the middle of the hardness range. There's also different kinds of paper that you can get into, which I'll let you read through this. This probably isn't super important, but these are some of the different types of paper that technically was used in the past, and some of it still today. But if you hear about vellum, that's the old school paper that drafters used. That is a really, really high quality paper. You can feel a difference between vellum and regular copy paper. That vellum is really high quality because it actually has cotton and wood pulp and some other synthetic materials blended into the paper. So if you pick up a piece of vellum, you can feel the surface of vellum is much better than what we would use like in an inkjet printer. It's just higher quality paper, and it erases nicer. This is still handy to know. All erasers are not created equal. So you will probably still do some sketching and erasing, at least with a pencil and an eraser. Anytime you design stuff, I like to sketch things out just to try and think about how they work, or especially if I'm reverse engineering something and I have something that I need to 3D model to try and design around. You're still going to be measuring things and sketching them and reverse engineering them a lot as a mechanical engineer. So it's important that you have a good eraser. Stay away from these ones at the bottom. They're all awful. For different reasons. The best is a white vinyl eraser. This is the same thing that comes in the end of a Bic mechanical pencil, but it's always just too little, right? They give you that little tiny nub of an eraser, and you mess up a couple times and that thing's used up. You can buy larger versions of these that are about this big. Just look for a white vinyl eraser on Amazon. You can buy them in packages, usually of like 3 of them. They'll last you forever, but they erase the best. They make the least eraser shavings, and they make a really nice, they clean up your paper really nice. So stay away from these ones at the bottom, like this thing, the Pink Pearl. I had one of these every year in grade school growing up. My mom would buy me the new Pink Pearl eraser at the beginning of the school year, and it's common you'd get that thing and you'd start scrubbing your paper with it, and it would tear a hole in the middle of your paper. These work really well, these art gum erasers, except they make tons of eraser shavings and they're really messy. And then these stupid things, these you may have seen these before. It's supposed to be like half the eraser is for pencil and the other half is for pen. And so the pencil half is really the same as a Pink Pearl eraser. They just didn't put the pink dye in it when they made it. And so it doesn't work any better than a Pink Pearl eraser. And then the ink side is made out of like a rock, I'm pretty sure. So when you go to erase your paper, it would just burn a hole in the paper. And so, yeah, the ink would be gone because there was a hole in your paper. So, you know, these are a scam to me. I don't understand how they're supposed to work. Like, you can't erase ink really unless it's an erasable pen that's made to be erased. But anyway, buy a white vinyl eraser. That's what I'm trying to say, I guess, is stay away from the stuff at the bottom. It will just leave you sad and depressed. White vinyl erasers are the best. If you're going to sketch stuff, buy one. These are handy also, triangles. A lot of people will use their ruler or a scale to make straight lines, but technically, according to the old school rules of drafting, you're not supposed to do that. You're supposed to use a triangle. And I think I've got some here actually. Hang on. If I look. I do. I've got too much stuff in my toolbox. Here are my triangles. So I don't use these a lot, but you know, I've got them in my toolbox that if I'm trying to, you know, sketch something out, you just use them to connect stuff. The reason you don't want to use your ruler is because when you take your pencil and you drag it across your ruler, it gets lead against the ruler. And then when you go to pick your ruler up to measure something, you get these lines all over your hand from where the lead was at on your ruler, and you look like a goofball. So according to the professional old school rules of drafting, these triangles, which hopefully you can see them on the video, these triangles are supposed to be your straight edge, not a ruler and not a scale. So this is what you use to connect dots or connect lines or make a straight line. And they're cheap too. You can get a couple of them, like, I don't know, these are probably $5 for both of them. They're cheap, but they're great to have around. Other stuff, you know, like a scale. We may talk about these later in the semester. Not super important right now, but you can use these to measure things on a technical drawing. A compass or a circle template is handy sometimes for drawing circles. Protractors, you've probably, you know, used a protractor in math class before for measuring angles. So these were used by drafters to try and create angled lines at specific angle measurements, along with dividers and tape. Here's some of the weird stuff that you don't see anymore. So this stuff did not carry over and you don't see it anymore. If you want to see how some of these things are used, I have a really cool video from an architect named Doug Pat, and he kind of shows some of these old school tools and how they're used. This one's really cool. I still have one of these somewhere. I think it's in my office at work on campus. This is called a lettering guide, and most people called it the Ames lettering guide because they were the most commonly known ones. But the way that it would work basically is you would take this lettering guide and put it against a straight surface, like maybe against your triangle. And it's a little, an Ames lettering guide is probably about the size of a credit card. And it has these little holes in it, and you would take your pencil and put it in these holes. So you'd put your pencil in one of the holes and drag it across your paper, and then jump it up to the next hole and drag it back, jump it up a hole, drag it over, jump it up, drag it back. And the whole time the lettering guide stays in the same spot and it slides across back and forth on a triangle or a straight edge. And since you're moving your pencil up each time a little bit as it goes back and forth, it makes these nice, perfectly parallel lines on your paper that you can then go back and put text inside on your technical drawing. So really all it is, it's a way of laying out guidelines for your text, but you can lay out a bunch of perfect guidelines like this in about 3 seconds, compared to using a ruler where you have to take a ruler and put it on one side and make a bunch of dots and then move it over to the other side and make a bunch of dots. And then you got to turn your ruler and try and connect them all, and it never turns out that good. The Ames lettering guide's really cool. And if you watch the video, I think Doug Pat uses one. Eraser shields are kind of funny too. Those didn't really carry over from the olden days. These, you basically, it's nothing more than just a piece of like stainless steel that's really thin. They're about the size of a credit card also. And you would lay it down on top of your drawing and just use it to protect stuff while you would erase. So maybe there's a line you need to erase, you would throw this down and erase through the line. And so you had your old school pencil sharpener, your drafting brush for wiping away eraser crumbs so that you didn't smudge it. Like you can't take your hand and wipe it across the drawing because it'll smudge all the lines. So, you know, some of these old tools you don't see anymore and they didn't really carry over, but that's what they are. Some of them are kind of funny too. Now let's talk about paper sizes. This is probably the most important thing that we need to talk about for the rest of this video. Paper sizes. you're going to run into these still, and they're going to be just as important now as they were before, because we're still going to be setting up drawings to fit onto paper. We're just doing it on the computer instead of on a drafting board, but everything still applies. So I got a short little video that I want you guys to watch that I did link right here. So this is, I've linked a lot of these videos in, but I do want you to actually watch this one. It's important to kind of explain this, but there's two different measuring systems for paper. There's US customary, or inches, that we use in the United States, and then there is metric paper sizes that get used in the rest of the world. So let's go back to the inch paper sizes. Everything in the US customary paper size is based on the A size piece of paper, the 8.5 by 11 inch paper that we all know that we run through inkjet printers and copy machines every day. So this is an A size, right? It's an 8.5 by 11, and we buy it in these packages like this. So we term that an engineering A size in the United States. Now, if I take those and I put them together, so if I take, two A size sheets and put those together, that gives me an 11 by 17, which is a B size, right? So two A's makes a B. If I put two B's together, that makes a C, two C's makes a D, and two D's make an E. Okay, or you can see if you chop it up into little A size, computer size pieces of paper, how many you would need. Now, even stranger, if you want to make this more confusing, which we love to do in the US customary system, there's two categories of paper technically. There's engineering paper and architecture paper. In architecture, A size is not 8.5 by 11, it's 12 by 9. So it's a little bit bigger than this. It's, half an inch wide, or half an inch wider and an inch taller. And then you can see the B size is a little bit different, and the C and the D and so on. So, those are sizes that would be used by an architect. Kind of weirdly though, like the architecture firms that I worked for, we didn't recognize the A and B sizes. The architecture firms that I worked for, an A size was still 8.5 by 11 and a B size was still 11 by 17. But the C and D sizes we used were the architecture sizes, so it's confusing, right? I guess the important thing to know about US customary paper is it doubles, right? Two A's makes a B, two B's make a C, two C's make a D, and it doubles each time. There is a huge problem with this though in the aspect ratio. The aspect ratio changes between sizes, meaning that if I take an A size, it does not scale cleanly to a B size. I'm either going to have to crop it or it's going to run off the edges. It does not scale perfectly up and down because the length and width ratios are different. Notice that an A would scale perfectly to a C because it has the same aspect ratio, and a C scales perfectly to an E. B and D scale nicely to each other because they have the same aspect ratio. But the US customary paper size system is a joke because a lot of times you have to crop or resize things to get them to fit, which is a hassle. Compare that to the metric system, which is perfect. In the metric system, every paper size scales perfectly to every other paper size, and you don't ever have to crop or resize things because the aspect ratio is always the same. So in the metric system, everything is based on the A0 paper size, and then it goes down from there. So the one you probably know the most from the metric system is A4. That's their equivalent to the letter size. It's not exactly the same, but it's really close. So just kind of for reference, an A4 is about the same as a piece of paper for us. Okay. So watch this video. It'll explain this idea a little bit better to you. But the reason I want you to know this is eventually we're going to set up drawings on paper in Autodesk Inventor. And when you go in there to choose your paper size, you're going to see all these options for different sizes of paper. And you have to decide, first off, what do all these mean? And second of all, which one do I pick? So if you don't know what they mean from the onset, it's really hard to pick the correct paper size. Scaling things, you'll hear this terminology as we go about like half scale, double scale, quarter scale. And really all it means is what is the paper size, or what is this object that I've drawn on paper, how does that compare to real life? Same kind of thing like you'd hear with model trains or model cars. We're going to skip through the hand lettering section here because I don't think it's that important anymore. But I will tell you, if you want to see something cool, this is kind of a skill. It's sort of like the secret handshake of old school engineers and architects that can still do this. Architects are pretty good at this still, but all these old school drawings that were done by hand, all the lettering on them was done by hand also. So Doug Pat, that I mentioned before, has a really cool video about how to write like an architect. And if you want to watch it for fun, I linked it in here. But it shows you this idea that architects use where they try to write almost like a typewriter, and they can write out in all capital letters almost perfectly over and over and over, and you can't distinguish that it was even written by a person. So it's a really cool, unique skill. It's very stylized, but it's something that older engineers and architects actually had to learn in college. They would take handwriting courses or lettering courses where they had to sit and just letter over and over and over. And so I threw some tips in here. Once you watch the video, if you want to try it, just kind of for fun, here's some tips you can try and use to improve your hand lettering. Mine's not great, but I've practiced a lot over the years and gotten a little bit better at it. So these are just tips. And then a cool book I found, if you're interested, if we ever get back on campus and you want to see this, I have a copy of this book. It's kind of cool. It's a book about hand lettering for architects and designers and engineers, and it's written by someone named, a lady named Martha Sutherland. But the cool thing about this book, and the reason I bought it, is I just thought it was so awesome because the entire book is written by hand. And so what she did is she went through almost like an impersonator, like Frank Caliendo would impersonate somebody's voice. Martha Sutherland goes through and impersonates people's handwriting. And so she goes through and she wrote the entire book. It's like probably a 100-page book about hand lettering. And she wrote the whole thing by hand, and then goes so far, even like in the back of the book, she starts to impersonate like famous architects or like famous architectural companies. She impersonates the lettering style that they used at their company on their drawings. And she'll do like, hey, here's Frank Lloyd Wright's handwriting. It's just crazy. So it's really, really cool to flip through a book that somebody actually wrote by hand, and just to see how good she is at the hand lettering. It's kind of like a cool, if you're into like coffee table books or just like, things you can just look through just to be interested in. This book's pretty cheap. I think it's like 10 or 15 bucks, but it's really cool just to sit and look through. If you're into like sketching or drawing at all, it's kind of interesting to look at. There's also a font you can get for your computer called Frank the Architect if you want to kind of cheat and type it in and have your typing on your computer look like architectural lettering. You can download the Frank the Architect font and kind of cheat at it, which is kind of funny. All right, so that brings us to the end of session number 1. So I have one assignment for you guys. So let's go back to Ivy Learn here. So hopefully you've gone through and you've done the welcome stuff already. You've already introduced yourself to the rest of the class. If you've done that, your only assignment for session 1 is there is an online assessment here. This is just going to be kind of a practice for you to learn how these online assessments work. You get a couple of attempts on this one. I think you get 3 chances, if I remember right. Yeah, you get 3 attempts on this one. So it's kind of just for practice. We'll do, 6 or 8 of these throughout the semester. But the first one is just kind of to get your feet wet and figure out how it works. Remember, every assignment that I give you guys is going to be due 1 week from the day I give it to you. So, this is going to be due 1 week from whatever day I unlocked the module. And again, remember the final authority on these due dates are what is posted in Ivy Learn. My video, as we go on in time, will probably get out of date and the dates will change. So whatever date is listed in here is the final authority on when this thing is due. So make sure you have it completed by the due date. But your assignment really for session 1 is do the welcome stuff, do the discussion board where you introduce yourself to everyone, try to download Autodesk Inventor from the home screen. If you click right here, download the Zoom client so we can have our Q&A sessions this semester and get to know each other and talk in person and answer some of your CAD questions as you guys get stuck on stuff. And once you've done that, go in and do online assessment number 1 where you can practice doing a quiz in Ivy Learn for the first time. Okay, so that's going to conclude my video for session 1. I got a little bit longer there towards the end, but hopefully this has given you, between our other video and this one, an understanding of what METC 107 is going to be about. We'll kind of get rolling here at the beginning. Within just a few sessions, we're going to be jumping right into Autodesk Inventor. So we're going to get into the software pretty quickly. Make sure you get it downloaded, but that's when the fun is really going to start, when we start using this CAD software and doing some 3D modeling. I love to use Inventor. I love to 3D model. It's one of my favorite things to do. And hopefully I can give you an appreciation for it also once we get to that point. But if you guys have any questions about anything from this first week, feel free to email me at jhamilton83@ivtech.edu, and I'll do my best to help you out through email. So good luck, and I will see you guys shortly in the next video later on. Good luck. See you later. Bye.